Hello to everyone, my name is Dordevic and I came from the Innovation Center Faculty of Mechanical Engineering in Belgrade, and I will show you, present you the paper with the following subject that you can see on the screen. It is about the Weibull probability distribution for off-cleavage fracture in transition temperature area for steel marked here on the screen. So let's begin. So what we want to present in this paper, we want to present the fracture of larger CT specimens are predicted based on statistical data obtained by using Weibull distribution for experimental results of smaller specimens. In this case, smaller specimens are CT50 specimens. Also, the effect of specimen geometry, thickness, actually temperature and fatigue crack initiation rate on fracture toughness are discussed. Fracture probability in this paper, actually cleavage fracture in the function of JC parameter for large specimens are discussed, as well as other factors that could have effects on the obtained data. So let's move on the next slide. Let's say a few words as an introduction on this subject. It is well known that the material characteristic, especially the toughness, change with the increasing or decreasing temperature, which means that depending on the test temperature, the same material may exhibit both plastic or brittle fracture or failure. The temperature interval during which the failure changes is known as the ductile to brittle transition temperature interval, or vice versa. The main problem of the experimental data for obtained experimental data in this sensitive area for ferritic steels are the scatter of the obtained data, and the main goal of all this research on this subject is to understand and describe the behavior of this steel, especially at the low temperature in the exploitation. Now I will say a few words about our experiments. We performed the experiment and the testing on the CT50 specimens. And in order to compare the results with prediction that we made using Weibull distribution, we did the testing of larger CT100 and CT200 specimens, and the testing was performed according to these ACTM standards, and the testing was performed at the temperature at minus 60 degrees of Celsius. CT specimens were made of reactor steel that you can see on the screen. This steel belongs to a group of A533 grade of steels, and this steel is used for manufacturing of pressure vessels and power plants reactors, and generally it's meant to work in extreme conditions. On the screen you can see the chemical composition of this steel as well as mechanical properties of this steel at the room temperature. Failure probability of CT50 specimens as a function of JC was represented using a two-parameter Weibull distribution. P in brackets J represents the probability that J for cleavage will occur at some value. The fitting was performed based on the experimentally obtained failure probability for CT50 specimens at the minus 60 degree Celsius temperature, which were displayed using a logarithmic coordinate system. The parameters of fitted Weibull distribution are calculated analytically via a least square method using regression analysis in the form given here, and the scale parameter of Weibull distribution is expressed as J value when P in the brackets J is equal 0.632. So this scale parameter theta is actually J value when P probability in the brackets J is 0.632. Now on the slide you can see the experimental results for CT50 specimens. As you can see, the JC values are pretty scattered. The JC value go from 60 up to 660 Newton per millimeter. Here you can see which specimens have B net 16 millimeters, and here as well you can see the displacement rate during testing. Now on your left side on this figure the Weibull distribution for B net 16 millimeter is shown, whereas on the right side the results and the Weibull distribution for B net 20 millimeters can be seen. The points here and here on the curves represents the JC values for the tested CT50 specimens, and the fitting was performed using analytical methods, as we say. Here we can see the two almost identical curves and shown failure probability of the attested specimens CT50. Now on the slide we can see direct comparison of Weibull distribution curves for fracture probability of both types of CT specimens. Here it can be seen that the specimen thickness affects the distribution, at least in the part where JC range from 0 to 500 Newton per millimeter, and in this region failure probability is higher for the thicker specimens. By unifying the results of CT50 specimen test with repeated Weibull distribution fitting, we get a new failure probability curve as is shown on this figure. The black line is the new Weibull fit for CT50 specimens. In this way, the effect of the thickness was neglected within the group of the same CT50 specimen for the purpose of predicting fracture probability in the function of JC for the larger CT100 and CT200 specimen at the test temperature of -60 degrees. The parameters for all three curves, Weibull curves here, were recalculated based on the CT50 Weibull fit three curves given here. In order to verify the obtained prediction curves and to get the better insight into the results, we have performed testing of 12 CT100 and 2 CT200 specimens at the same the temperature as CT50 specimens in accordance with appropriate standards which we have mentioned before, and the obtained results of the testing are shown here in the table 4. Direct comparison of JC values obtained by the testing and the prediction of their failure are shown here. The Weibull distribution and the comparison. We can see that on the larger specimens the scatter of the results are smaller one, and it can be seen that the diagram that the Weibull curve shows a good agreement with the experimental results. Now let's do some discussion on these results. The cleavage fracture probability diagrams that we obtained for larger CT specimens represented by Weibull distribution as a function of JC can be used to show the effects of specimen thickness and on its expected values during fracture. And based on these experimental results and the probability diagrams obtained in this research by using statistical method of data manipulation, it is quite possible to obtain a relatively accurate prediction of behavior of this still at a low temperature range. And that will be it. Thank you for your attention. If you have any question, I'm here.